Glad is going to talk about phase diagram of underdoped cuprates.
It's an ambitious title. Okay, well, is this too loud? It is. Okay. So I would like to thank the organizers for the opportunity to talk here at this nice conference. I'm also happy to be here because this is my first time in Brazil. So I'm excited about that. So I will talk about some of the recent results from my group at the National High Magnetic Field Lab in Tallahassee, Florida. The experiments were done by a former postdoc, Jen Zhongxi, graduate student Paul Beatty, on truly excellent single crystals that were grown by Takao Sasagawa, who is in Tokyo. So we already had a very nice introduction to cuprates in the first talk, where it was also pointed out that even after 30 years of intensive research, some of the key questions in the physics of cuprates remain open, and one of them was addressed in that talk. So from the early days of the studies of cuprates, people have been using magnetic fields to suppress superconductivity and to reveal the underlying normal state. But up to this date, even some basic questions, such as the value of the upper critical field in cuprates, remain controversial, and the interpretation of the data is contradictory. In addition, in recent years, there has been a lot of experimental effort that established that in all hole-doped cuprates, in the underdoped regime, some kind of charge order takes place, and the interplay of these charge orders with high temperature superconductivity and high magnetic fields is also one of the open questions. So this talk will focus on two very basic questions. And before I show you our work, let me illustrate some of the ongoing controversy. These are a couple of examples from the recent literature. So in one group of experiments, the upper critical field was identified as the field where the vortex solid melts at 0 temperature. Now, in another set of experiments, on exactly the same material, exactly the same doping, it was argued that vortices are present even up to much higher fields, well beyond the field, well beyond the quantum melting field of this vortex solid. And in fact, that vortices persist up to fields that are experimentally inaccessible. So these experiments were done on YBCO. There has been a lot of work on that, and it has been established that in that material, at low temperatures, well, low enough so that superconductivity is suppressed, one observes the development of this kind of long-range static charge order at high fields. But the phase diagram at these low temperatures is not well established, and it is also not clear how this charge order is related to a shorter range charge order that is present in this material already at 0 field at high temperatures. So since most of the work has been done on YBCO, and because all this is unclear, in order to answer the two questions that we posed, it would be helpful also to look at other cuprates in which short-range charge order is present already at 0 field, but this longer-range charge order does not appear at high fields. Also, we want to be able to have very low TCs in order to be able to hope to have that experimentally attainable magnetic fields are high enough to fully suppress superconductivity. Also, since we are interested in what happens in the 0 temperature limit, it is always necessary to have to do experiments over a sufficiently wide range of temperatures to be able to make reliable extrapolations to 0 temperature. And of course, one needs probes that are sensitive to vortex matter. So we have accomplished all of this, and before I show you our results, I would like to remind you of some of the things that we know. And what we do know is that cuprates are type 2 superconductors, which means that the magnetic field penetrates the material in the form of a solid lattice of vortices up to the, in this mixed state, up to the upper critical field. We also know that thermal fluctuations can melt, or do melt, this vortex lattice into a vortex liquid such that this vortex lattice is suppressed below what is now a crossover field HC2. So the resistivity of this vortex lattice, as we all know, it's a superconductor, so resistivity is 0. And the reason for that is that vortices are pinned by disorder. Now, if the disorder is sufficiently weak, which is the case of cuprates, then this disorder will only distort the vortex lattice without introducing dislocations. And this is an actual SEM image of such a state. This is called a Bragg glass, so this is experimentally well established by now. This Bragg glass can be melted via thermal fluctuations into a vortex liquid, which has lots of dislocations. It's amorphous. Or at very low temperatures, it can be melted by increasing the disorder or by increasing the magnetic field, because both introduce topological defects. So now in the Bragg glass, or this vortex solid, we know, as I said, the resistance is 0. We also know if we increase the current sufficiently beyond some critical current, then we start measuring, the resistance. So this means that the voltage current characteristic of a superconductor is nonlinear. We have this finite critical current. Now, in contrast, in the vortex liquid, we measure finite resistance in the limit of 0 current. So there is no critical current. You measure resistance, finite resistance. However, as we lower the temperature, at low temperatures, the effects of disorder will start to dominate, and then this vortex liquid will become viscous, it will become sluggish, and it will slow down, and it will freeze into a vortex glass at 0 temperature. So strictly speaking, this vortex glass becomes a superconductor only at 0 temperature. However, at low enough temperatures in this regime, one observes also, even though the resistance in the 0 current limit is finite, one observes the nonlinear voltage characteristic. So the effects of disorder in general, on these general grounds, are expected to dominate at low temperatures and high fields, which is precisely the regime that is relevant for the determination of the upper critical field. And we can see from here that the difference between these different phases, or let's say regimes, not phases, is in their behavior in the limit of 0 current. So I will just mention here that in order to be able to distinguish these regimes where low temperature regime where disorder dominates, and the higher temperature regime that is non-ohmic and ohmic behavior, we are going to call this vortex glass, even though strictly speaking it freezes at 0 temperature. So since the difference is between these different regimes in the low temperature limit, we want to be able to measure the response of the system to a small external force. In particular, we want to study voltage current characteristics at low excitation currents. So this is what we have done. We have measured both linear and nonlinear transport to be able to identify these different regimes.
The blue dashed line, this is supposed to be a crossover line, right?
Yes, I think it's a crossover. In our case, as you will see, I think it's a crossover, but in principle, it's an open question. But yeah, it's a crossover. Okay, so this is so the materials that we have looked at are from this family, lanthanum-based cuprates, which have, as was already noted earlier today, low TCs. So these are the two materials. They're phase diagrams. And in these materials, the TCs are low, as you can see with these red symbols. And it is also known that in 0 field, around this 1,8 doping, charge orders develop in the form of stripes, which alternate with the charge poor antiferromagnetic order, the spin stripes. Shown here, this is a sketch, and the arrangement of these stripes also, they're rotated by 90 degrees from plane to plane. In reality, these are short-range stripes, so the correlation length is these materials is of the order of 100 angstrom. So the vertical lines show the dopings of the two materials that we looked at. So this one, LNSO, is at 1,8. This is where the TC has a minimum value. It's less than 4 Kelvin. And the other one is at slightly lower doping, LESCO. So in this material, stripe correlations are weaker So the TC is lower than the onsets of spin and charge stripes, and all of these temperatures are much lower than the pseudo-gap temperatures for these two materials. I want to note that these our crystals were astonishingly stable over a period of 2 to 3 years during which this study was carried out. So their properties did not change with time, which indicates that the doping was stable. It's a signature of a high quality of these crystals, and you don't always see this, unfortunately, in cuprates. Without going into too much detail, I'll also mention that we have not found any evidence of extrinsic inhomogeneities in these materials, and compared to the samples of the same material, this is just an example, Orlesco, ours actually have a lower disorder. So the low TCs of these R materials have allowed us actually to explore a much larger energy scale window compared to previous studies. And to illustrate that, we have made this sketch, which shows the lowest temperatures and highest magnetic fields reached in various studies on this topic. And this is our results are shown here. Clearly, you can see that we reached the lowest temperatures and the highest fields, but not only that, we have actually explored the highest range of parameters. So we've mapped out the properties of the system in this rectangle here for this material, for example. Whereas the previous study on exactly the same material explored only this window of parameters. Okay, so let me show you some data. So first we measured linear transport or transport in the zero current limits, in particular in-plane magnetoresistance. So here are the raw data, and I will show mostly data for this material, but they are qualitatively the same for both materials. So what we see at high temperatures, it's flat, doesn't really depend on the magnetic field, and then as you reduce the temperature, you start seeing positive magnetoresistance, which means that you're suppressing superconductivity. But as we lower the temperature further, we see that this broad peak actually becomes sharper, and it's followed by a wide range of fields where one observes a negative magnetoresistance. So this is actually very surprising because it has not been seen in cuprates. People have seen only positive magnetoresistance, with the exception of this early study by Ando and Bobinger, where in LSO, where at their lowest temperature and very high fields, they observed a broad peak. This obviously represents some characteristic energy scale where something changes. So what one can do is, and we see that it depends on the temperature, the position of the peak, so we can track this position as a function of temperature. So we can use the same data to extract the temperature dependence of the resistivity for different fields. So here are, this is what it looks like. You see that as we increase the field, TC is suppressed, so you can map out the dependence of the TC on the field. We also see that at some point this temperature dependence starts to develop a peak, which also depends on the magnetic field. So this is another characteristic feature at this point that we can track. So before I continue, I'd just like to point out this really striking, I think, fact that these different curves start to split into two families, those that become superconducting and the others that do not want to be superconducting, when the normal state sheet resistance is essentially the same as the quantum resistance of Cooper pairs, h/4e squared. So this is what you expect in 2D films near the superconductor insulator transition, driven by the loss of phase coherence where Cooper pairs persist on the insulating side. Now it is striking because these are bulk materials. So we have, I don't know, million layers, and this looks much better than it does in 2D films. So this suggests that at lower temperatures, the phase fluctuations might be playing an important role, and we see the same thing in both materials. So anyway, we have these two characteristic energy scales. We have peak in the magnetoresistance. We can start mapping out the phase diagram. This is actually the result. So the temperature is on the vertical axis. Note that it is on a logarithmic scale. We have more than 3 orders of magnitude The black symbols are the TCs as a function of the field. So this is the region where the linear resistivity is 0. Green symbols are the peaks in the magnetoresistance, and the blue symbols are that peak in the temperature dependence of the resistivity, and the phase diagrams are shown for both materials. So we see that this vortex solid is separated from the normal state, and I will show you the data later, by a wide range of fields, by a regime that we identify with the vortex glass. So what is the evidence for that? Okay, so what we find in this regime that we call the vortex glass, first of all, is that the linear resistance phenomenologically is described best by a simple power law dependence. And this means that in the 0 temperature limit, the resistivity will become 0. So the system will become a superconductor, which is what one expects when vortices freeze at 0 temperature. So then we also studied, as I said, nonlinear transport. So in this regime, here is an example of what the data look like. So this is a differential resistance as a function of DC current and 2 different polarities at 3 low temperatures. So you can see, for example, at 17 millikelvin, these are the black symbols. The resistance is still finite at 0 current limit, at 0 current DC. However, the voltage current characteristic is strongly non-ohmic, which is what one expects in the vortex, in the viscous vortex liquid that we are calling, for convenience, vortex glass. So we have performed these measurements over a wide range of, well, the entire range of fields and temperatures, and here is just one example. For example, at the lowest fields, the resistivity is 0, because here we are inside below TC and we are below the critical current. But when we get into this vortex glass regime, we are measuring finite linear resistivity, but the VI is nonlinear, and if you keep increasing the field further, you know, I know this is hard to follow, but basically at some point, at some field, these curves will become flat. So the transport is ohmic, and you can identify the field that we call H star, which marks the transition between the non-ohmic regime, these are H star, these red symbols, and there are some here, non-ohmic regime at lower fields, and ohmic transport here. So, so basically what we find are 3 experimentally distinct regimes, as one expects, as I described at the beginning. Here resistivity is 0, we have critical current, and here the resistivities are finite, linear resistivities, but the VI is non-ohmic, and here we find ohmic behavior. So we also have these points here, blue points. They're determined at high temperatures, as you can see, from the region where magnetoresistance is still just positive. And this is just using the same method that's been applied before. Basically what people find that at high temperatures, magnetoresistance is positive, and high enough fields it goes as h squared, which is what you expect in a metal. So you can identify this field where it starts to deviate from that behavior as the onset of superconducting fluctuations. So these are these blue points, and there are just a couple here. So by doing the usual quadratic in temperature fits, we see that this extrapolates really surprisingly into this same field where non-ohmic behavior vanishes. So this supports our identification of this star, of this field H star in the limit of low temperatures as the upper critical field. So what happens here in this state where, based on these measurements, we do not see any evidence of superconductivity? So the normal state, this is what the temperature dependence looks like. This is a log scale. So it has an insulating-like temperature dependence, which is logarithmic dependence on temperature. So this has been seen before, like in early studies on underdoped LSCO. But what is new here and what is different is that here we see, as we keep increasing the field, this slope, this insulating-like behavior becomes weaker. And the black symbols here are these slopes which extrapolate to 0 at some high field for this material above 55 Tesla. So this suggests that at even fields higher than this, the material will become metal. And the same result is found in other materials. So this data suggests that the high field ground state of these striped cuprates is a metal, which is different from the underdoped LSCO, where the data suggests insulating behavior. So of course, we still don't understand, why this is logarithmic, and don't understand the properties of this state, and this is also an open question, what happens at higher fields. So this all will have to be subject of some further studies. So coming back to these phase diagrams, I'd like to emphasize that the agreements between our results obtained from nonlinear transport and from linear transport, and in particular, especially all these different data agree at lowest temperatures, including this position of this magnetoresistance peak. So this tells us that this magnetoresistance peak is the field scale for the closing of the superconducting gap. And this is very similar to what people have found in 2D films of conventional superconductors, such as indium oxide. This has been, subject of a lot of work over many years. And I think the conclusion that has been reached is that is basically the same as here, that this peak corresponds to the field scale where superconducting gap closes. So that means also that here, where we still see this peak, we have access to bosonic regime where transport is ohmic. So we identify this with the vortex liquid. So this is consistent with the general picture that I described at the beginning. At high enough temperatures, you have vortex liquid, you cool the system down, and vortices slow down and start to exhibit some kind of glassy behavior. So what have we learned from here? Okay, so let's see first what happens at zero field. We find the onset of the phase fluctuations dominated regime at temperatures that are several times higher than the zero field TC. So this is in contrast to what some people have been claiming, but nevertheless, these temperatures are still much lower than the pseudo-gap temperatures for this material. So in these experiments, we do not find evidence of pairing at such high temperatures. Nevertheless, this is a very wide, very broad regime where phase fluctuations dominate, and this can be attributed to several factors. One is the effective two-dimensionality of these materials, where one expects to have a BKT transition at zero field. Also, we know that in these materials we have intrinsic nanoscale phase separation. We have these short-range charge and spin stripes, and we know that in general, one can have, in the presence of competing interactions, one can have nanoscale intrinsic phase separation, even in the absence of disorder. And it is also known that even the homogeneous disorder may give rise to spatially inhomogeneous superconducting amplitude in the material, and this has been observed in some cuprates, such as with using techniques such as STM. So the upper critical fields that we find for these materials are consistent with such high temperature for the onset of the phase fluctuations dominated regime. I also know that the values that we found are much higher than in previous studies. For example, for this material, it was claimed that the upper critical field was less than 8 Tesla, but the study, as I said, was done at much higher temperatures. So that field basically kind of corresponds to this change from the vortex glass to vortex liquid regime, non-ohmic to ohmic. So this really underlies the importance of going to lower temperatures, because we can see from the phase diagrams that this vortex glass regime broadens significantly as the temperature is reduced. And we attribute this to the effects of disorder at very low temperatures, which melts this vortex solid into this vortex glass regime. So basically, these upper critical fields then would correspond, that we found would correspond to the upper critical fields of the clean system. So the question is, okay, you can say this is all very nice, but what are the implications for the other cuprates? Well, this is an illustration of what one would, or some people would expect, is that the effects of disorder obviously have to become important in low temperatures. And so even if the material is very clean, such as YBCO, it is established that it does have some disorder, one can expect that its effects will be amplified at very low temperatures. So one really needs to go to much lower temperatures, which was not done, and apply a small external force, which also has not been done up to now. And of course, one needs to use techniques that are sensitive to vortex matter. And as far as magnetoresistance goes, as I said, they may observed only positive magnetoresistance. So these are a couple of examples. So in other words, the peak has not been reached, although here at low temperatures you can see that, something that could become a peak. So what would be needed, I think, is to measure YBCO, to perform a similar study on YBCO with a relatively low TC, so one can hope to be able to reach this regime, the upper critical field, basically, and see how the results compare to these results on cuprates. So how do our results compare to other studies? Of course, as was pointed out more than once, this is an old field, and people have been trying to determine superconducting gaps in these materials, in cuprates, using all kinds of techniques. So this is from the review paper already 10 years ago, and it shows the results from various spectroscopic probes like ARPES, STM, and so on several different families of cuprates. And you can see the results for the superconducting gap all basically can be described with this expression. So the superconducting gap they found is 5 times zero field TC. So for these materials, this is a much larger energy scale, as you can see here, which suggests indeed that the upper critical field may be experimentally inaccessible. Now, if we use the same expression and plug in our low values of TC, this would give a much smaller energy scale, which is of the same order as our upper critical field. And this agreement is, I think, striking, because in these studies, in these comparisons, they were not even considering these family lanthanum-based cuprates because they have much lower TCs. And they didn't want to make any normalization, so they were just looking at the absolute values. So finally, what are the effects of charge order? So as I said, these two materials have a different strength of stripe correlations. The stripes are stronger here, but the phase diagrams are qualitatively the same, the vortex phase diagrams, which is what we studied. And in fact, the qualitatively the same result was found in very underdoped LSO, with which the charge order has not been found yet, although people have looked, and if there is any, then it must be very weak. So we see that that the pairing strength in underdoped cuprates from this is not very sensitive to the details of these competing charge orders, although the precise values may depend on that. So basically, this is the summary. So we were able to explore the previously inaccessible regimes, which allowed us not only to map out this vortex phase diagram, but also to probe this unusual high field normal state. By relying on transport techniques, we have been able to obtain quantitative agreements between our results. And so the key results found here are, I think, that the intrinsic disorder plays a key role in understanding behavior of the vortex matter in the zero temperature limit. And I think our results also reconcile the results of different experimental techniques. So this is the value of superconducting gap for all experiments. And it is, as I said earlier, particularly striking because transport in a magnetic field is very different from these local spectroscopic probes in zero field. So we think this provides a unified perspective on the strength of pairing in underdoped cuprates and on the superconducting phase transition. So thank you very much for your attention.
Very nice. Did you try to also measure out-of-plane resistivity, and do you see any features that correlate to what you see in the plane with rho AB and rho C?
Yes, we have measured the out-of-plane resistivity, and I mean, I could show you the full phase diagram, but maybe it will lead to too many questions. So yes, I mean, the anisotropic, I mean, this supports actually these are the real phase diagrams. I mean, this was the real too, but these are the data, and I don't have time to go into details. But basically, we have measured anisotropic transport, and we find that in this high field regime, beyond this, what we identify as the upper critical field, it does not depend on the field, and it has the value that is basically the same as the value at high temperatures. So which supports our conclusion that we are in a normal state. And then, you know, we have these are actually the red points are the results from the anisotropy. So we start seeing the anisotropy as we, you know, start getting superconducting fluctuations. So.
I guess you showed this famous logarithm as a function of temperature for the high field data.
Yes.
Is there any scaling that you can do with the magnetic field to understand how this changes? In other words, you say the slopes go to 0 for H.
Yeah, I mean, this is all we've done.
Yeah, and so it goes. So you would say that. So can you reduce everything though to a single curve then, just with that?
No, I mean,
you would still need a prefactor, which is field
dependent. Yeah, because the slopes are different. I mean, I suppose, but.
Okay, so the slope is.
Yeah, yeah, I mean the slopes. I mean, so it looks. Yeah, I mean they're starting from the same point at high temperatures. So you cannot.
You cannot collapse everything. You cannot collapse everything onto a single function.
Yeah, you cannot. Yeah.
Okay.
Hi, very nice presentation.
Oh wait, the quiz. Oh, okay. I didn't see who was asking the question.
Okay, so one question. Your data shows the trajectory of this H peak shows a non-monotonic behavior. Very interesting non-monotonic behavior.
Yes.
So now you also compared or actually showed one data from old indium oxide, where the peak position did not show much of non-monotonic trend. So any you'd like to comment on that? I mean, those were probably conventional superconductor as opposed to yours. So
yeah. So this, I think, this goes from this. I think this corresponds to this higher temperature regime, right? Goes from higher temperatures to lower. No, wait. I'm not sure. No, this is.
As you go up, you are decreasing temperature in this indium oxide.
Yeah, the field is going down. So it's like this, corresponds to the higher temperature behavior. No, I mean, yeah, this has not been, I think, observed before. And I have talked to, several people in this field just to make sure I haven't missed anything. No, I mean, I don't know why this is happening. Yeah. I mean, there are, I was able to find some paper about superconducting fluctuations, looking at different corrections, and it shows that it is possible to have some kind of non-monotonic reentrant behavior as a function of temperature for, certain range of parameters, but I have no idea whether this is relevant to this or not. And yeah. You have you have an answer to this?
No, but I have a question about the same part. Right? So your phase diagrams imply that there is reentrance.
Yes.
Which looks like you go from normal as you lower the temperature. You go from normal.
Yes.
You go to the vortex liquid. And back to normal.
Yes.
Right? So is there any understanding of why this is happening?
No, I mean, as I said, okay. As far as I know, no one knows. I found one paper which suggests maybe something like this is possible. This was paper by, I think, Larkin, Gaitsky, some contribution of, calculating different contributions to superconducting fluctuation in the disordered system in a magnetic field. So these are the two important things. But I have no idea whether, again, this is relevant to this case or not.
And this boundary between red and yellow, this is just based on that peak position. So I'm trying to grasp what the physical meaning is of this reentrance in terms of observables, measurable quantities.
Well, I mean, observables, I mean, okay, so this is, we have negative magnetoresistance here. This is where we have this logarithmic temperature dependence. Right. And this is where, you know, we have metallic behavior. And actually, oh, okay, let me go to the you know, real phase diagram. Because here, this color actually shows the slopes of the temperature dependence. So blue is metallic, and this is insulating-like. Right. Okay, so maybe this helps. So here, this is insulating-like.
Yeah, but there's no change across the green dots, right? This is all insulating-like, right?
Yeah. Now, let's see if I look at the... Yeah, I mean, it's insulating-like. So, I mean, it's probably, okay, I would have to see where it's actually nice logarithmic fit. So maybe it's not a nice log here, but it's insulating-like. Because, you know, here we have obviously have crossover to metallic, like at fixed temperature. So, you know, it's probably, yeah, so the peak was here. So I think just a crossover.
These are real phase transitions.
Okay, no, I think they're crossovers. So this is a phase transition, black symbols, and I think phase transitions are in the zero temperature limit. I think these are just crossovers. Yeah.
Is this strange onset as function of temperature? I'm asking the same question about the temperature dependence. When you add field, this onset, this hump, becomes stronger and stronger.
Which hump? I mean, we have more than one, so that's okay.
The resistivity as
peak in the temperature dependence. Yeah. So it shifts to lower temperatures, and yeah, I mean, these are the blue symbols.
No, I'm thinking about resistivity as a function of temperature.
Yeah, yeah. So and it becomes, yeah.
It develops stronger. These people have seen also in iron selenide. In iron-based superconductivity, people see the same. It's very dramatic there as well.
Okay. So I mean, what we find basically below that peak, you know, you get this vortex glass behavior. So I mean.
But I'm a little bit confused because I think iron selenide is supposed to be quite clean. So
well, I mean, I don't know what people mean. You know, they're saying
is it necessary for this behavior?
Well, okay, I don't know about iron selenide. These are doped materials, and so I mean, there is always random. I mean, you have disorder.
Right,
so
iron selenide is undoped. You don't need to dope it. Clean iron selenide, you don't dope it. It's already superconducting.
Well, I mean, I cannot, you know, I cannot explain. I mean, I don't know about iron selenide, so I cannot tell you why. Right. I know why. You know, we have the data for this, and the data are all consistent. So I don't know.
So my question is, how likely this physics is really disorder driven, or is it possible that there is actually some kind of intrinsic behavior that also gives you this physics without resorting to disorder?
Well, I mean,
from experiment point of view, can you?
Well, I mean, disorder becomes dominant at low temperatures, but you still have this, you know, vortex liquid. Even if you didn't have disorder, you have, you know, vortex liquid behavior. Yeah. So, you know, the effect, again, if you're not at very low temperatures. Now, I don't know whether, you know, this would affect this boundary here or not. I mean, this is supposed to be the upper critical field for the clean system. If there was no disorder, this would go all the way up here. So yeah, it should remain the same. So I think it will affect, I think, only voltage current characteristics, whether they're linear or non-linear, but.
Do you have any electrical Hall effect data in the phase 2 and phase 3?
Yes, we do, but we still need to write the paper up. Okay, I mean, here what we have, everything I think can be explained with superconducting fluctuations or although other people have offered the other interpretations, but we have this, you know, phase diagram to kind of correlate our whole data with that. And, you know, there are some unusual things going on here, but again, this is not written up yet, and I learned the hard way not to talk about unpublished data too soon.
More questions?
Maybe just the last one, because you have some incommensurability. If your vortex lattice is triangular and your stripe order is squarish, then you have some kind of incommensurability. Maybe when he refers to some intrinsic mechanism is, despite the fact of having point-like disorder or columnar-like disorder in rather earth-doped ones, you will still have something intrinsic that might be important.
It's possible.
Right?
Yeah.
This
yeah.
incommensurability.
Yeah, that's definitely true.
Okay, if you don't have any further questions, let's thank the speaker again and resume at 2. Yeah.